Hey guys, did you know that these things exist? Basically video walkie-talkies, where you can have a wireless transmission to one and another and have your kids play around with them, or yourself. Pretty cool, right? But what is even cooler now? You can fully hack them and get Doom onto it and shoot a few rounds. And while it is a bit hard to control, it fully works. And if you want to know how I made it, and if you want to build it yourself as well, just keep watching. Hey guys, a while ago, Big Clive did show a teardown of these walkie-talkies, and of course I had to also get them, because the inside of them and the price is really interesting to tinker around, and of course, you know it, to play Doom on them in some way. Overall, it's like a 20 euro, some even 15 euro order from Amazon, even that cheap, or from Aliepress. And there are many different versions. I also got just like a similar one, just to compare the insides and also like the outsides. And overall you get like the manual, USB-C, charging cables, and like the hooks. And how they work is really you have like two cameras, or a camera in each device, and a display in each device, a microphone, a speaker, and like a battery. So when you turn them on, it's basically like a walkie-talkie but on Wi-Fi basis, as far as can be told right now. And they do search with some custom protocol for each other. And if you now just call one and another, you can basically see and also like speak from one to each other. You can go back into the menu, and these are even a bit more advanced than the other one. I will show it in a moment as well. You can even send like chat icons or messages, basically like smileys or a voice note or an image. So there's really like a data protocol running inside of it. And you can also really like take pictures, which will be saved in the internal memory. You cannot really get them out, I think via USB, but I haven't looked into it. And other than that, you have on this even cheaper model, I think this was like 15 euros and the other ones were like 20 euros. Here you really have just that, so no extra function really, and just the video walkie-talkie. And of course, we are here to take a look inside of them as well. We will just also start with the cheaper one. And on the Big Clive video, we already saw that it's a TXW818, which is very comparable to an ESP32 in terms of power and functionality. And it has like, in this case, 2 MB of external flash. And in the other more expensive one, you have 4 MB of external flash, which is also understandable because it has more functions with the chat thingy. And Big Clive really did only open it up and did not look any further, but we will do so. So this is the cheaper one, and you can really see like, okay, we have this TXW818 C04F. C stands for the pin amount, like 64 pins in this case. 0 means it has no internal flash. 4 means it has 4 megabyte of PSRAM inside, and F is a number. No, not a number, a char. I haven't really found out what this is for, but that doesn't really matter. You have a front end for the Wi-Fi, so you have a bit more range. You have the external flash of 2 megabyte in this case. You have, this should be an amplifier. You have like a voltage regulator, the battery charger. You have the camera here and a speaker and a few buttons. And of course the battery with 650 milliampere hour. All not so interesting really, but just to show it. Now let's also take a look inside of the more expensive one. And like more expensive is really not that much money actually, if you even get like 2 devices. So one is just 10 euro, more or less, whatever you do with them, of course. So let's also open it up. And here it's very similar to the other one. Let's remove the battery. We have here like an unknown battery actually. What is it? 800 milliampere hour. Then we also have the chip here, but they lasered away the markings, which is okay. But since we have the other one, we know it already, and yeah, it doesn't matter. They also removed the marking of the front end. Here we have again the speaker driver, the external flash of 4 megabyte, the camera, the speaker, the charger here, the voltage regulator. So it's very similar, but it's still different. And what's even more interesting is that also the Big Clive version is again different from each other, while they all do the same thing basically, but either there is sitting someone in China and designing all on their own, or they really design the same board 5 times for different customers. Just moves things around also. It's very strange and I don't understand it fully. Otherwise, on this one also, the external flash has the so-called scrambling enabled. It's the SPI reader from the SoC has an active scrambling algorithm that can be used. So if the SoC reads the flash, everything reads fine because it's just a pass-through. And if you just dump the external flash and save it, it is scrambled to a non-readable point, and you have to XOR all the values with some address-based XOR key. And if you connect to the debug header, you can see here, and read it out by the chip itself, there is no scrambling active, so you can just dump the flash that way anyway. So it's some kind of security they did there. For once, the removing of the markings, and also, of course, the external flash scrambling. So they tried to hide the workings of it a bit. On this one, it's really just readable. Also, you can just dump the external flash and go on. And next, let's try to hook up a debug interface, or to the debug interface, to the UART interface, and see what it does. What I can also tell is that on the more secure one, also the UART interface is not active from the firmware, so you cannot really read anything. But on the cheaper one, you can just hook up the UART converter and read out the status of the device. So here it's also like a bit more secure. And let's get to Doom, of course. So here we go. This is now my development setup. I have for once connected a USB to UART converter. This helps to read basically debug messages. We have a debug interface connected. I will talk about this in a moment. And we have the Power Profiler Kit 2 from Nordic installed or connected to really see what is going on inside of the board on power level. So we can really just see what the chip is doing, if it's doing some calculations only based on the power consumption, which is helping a lot in these reverse engineering projects. And mostly it is now connected via this 4-pin header behind the LCD connector. And this is, in this case, the JK200 board. And we have ground, we have port A9, A10 and A8. And the two interesting pins is A9 and A10, which you can see is here now connected to the debug interface clock and I/O pin. And in case of this board, it is also the UART interface they use. So we can read basically the debug messages. On the other board with the lasered chip, there's also the pin header, which you can see here. And it's basically also just bringing out the debug interface, which is quite nice. So this debug flasher is more or less from the electroda.com page. They also note from where it is, like here. And this is basically a clone from the original manufacturer programming interface, which is quite nice to have it that way and don't need to buy like a 50 euro flasher, and you can just flash a modified firmware onto this blue pill board, which is quite the nice board, especially a few years ago. And other than that, on the manufacturer page, we can also get like the SDK to download, which is pretty nice. And these are like 20 megabytes in size. I worked mostly now with the FPV SDK. And you also need like the original compiler, which you can get on a different page. It's called the CDK compiler, IDE, GUI, whatever. And other than that, if we now turn on the board, we can see like the debug outputs, and we can see the power consumption, and that is still everything working so far. And I dumped out the flash. I did put it into Ghidra and added the core specifications from a repository, and was able via the SDK to reverse engineer quite a lot of the firmware. And most important, or the most complicated one right now, is really like the LCD and the camera, because these are custom parts in this case. They are not available in the SDK, but by reverse engineering the stock firmware, we can just basically get them also to work. And I have a quite far custom firmware right now, where you for once see here the LCD pinout I added. And also, let's try to find the added camera, for example. So we have the custom camera, which is reverse engineered out of the firmware. And let's see if we can also find the LCD driver, which should be in the bus folder, and add the LCD, yes. And there we have now the GC, no, not the GC, the NV3031A, which is also basically now added by reverse engineering the firmware. And this overall is everything that is was needed to get to a functioning state. And what else? To flash this now, we have to do a trick basically, because the original firmware is deactivating the debug interface. And by now connecting the SWD interface basically to the flasher, we would be able to flash it if the debug interface is not deactivated. But we can now turn off the power and bridge the capacitors, of course, and also bridge the SPI interface of the external flash, and now turn on the power again to be able to disturb the loading of the firmware. So the chip is basically stuck in a loop and has no firmware running, so it can also not deactivate the debug interface. And I will try to do it now with one hand. So I bridge it, I turn on the power, yes, and now it does not fully boot. And also the current consumption is basically halted at this level. If we now go into the SDK and IDE and just flash a new firmware, we can see that the flashing is running. And also we can see the power consumption is fluctuating a bit, so it flashes. And after the flashing is done, it will boot into the new firmware. And as you can see now, we have a working display and a nicely menu, an LVGL menu, which is the example of the SDK basically. And also the buttons are working already quite a bit, but not perfectly, because these use resistor level detecting of the buttons, and the resistor values are different from the firmware the devices use, or the SDK uses different values. And we can also basically enter a menu by holding one button. And there we can see that also the camera is working fine. So even that is already working. And now basically nothing is stopping us from running Doom on it. Overall, the SDK is quite convoluted, but okay to work with. It's really not nice to fully understand what's going on, or basically have an overview of everything, while everything is also so stuck behind the HAL or the SDK libraries and so on. But it works out. So next step is now to remove the original menu, port Doom into it, connect the buttons correctly, maybe even support audio, because if we now have a speaker, why not? Yeah, see you in a moment. Here's the very first and fully beta version of it. So let's turn it on. And we have for once a little screen. And then normally the Doom demo screen is running. But if we now go into the menu and start the game, we can already see something is happening. And it's a bit hard to trigger the buttons, and you can see how it's jittering right now, but better than nothing. And if I press the other button, we can also turn around. And would you look at that? Doom fully running on both hardware variants, for once on the 2MB flash version and the 4MB flash version. Beforehand, everything was running fine on the 4MB one, but on the 2MB board, we really had issues fitting everything in. What the solution is now to just compress the Doom file from around about 1.4 megabyte to like 500 kilobytes onto the external flash. And on boot, it will unpack the compressed file in the PSRAM. So if we now turn off the board and turn it on again, we can see that it is loading the file first to get it into RAM, and then can start it. Also, the firmware will now detect on boot how much flash is available, so it can set the correct resistor values for these buttons, because these are a bit different in between. And if we now basically go into the menu and start a new round, we can go forward and backward. And if we hold the other button while doing so, we can rotate, and we can of course shoot again. And a little Easter egg is the camera is showing in the middle. So if you are playing and have basically your face against the camera, you will be the player, as it should be. So now I will put everything back together, and then we can shoot a few rounds. Finally Doom on a Walkie Talkie. So yeah, that's all for today. I hope you find it a little bit interesting and maybe you can build one yourself. I will put the source code in the description. It's a GitHub repository with all the necessary parts except the blue pill flasher, but it is linked there as well. And yeah, if you see a few more different variants of it, which is very likely because they are floating so much around, it might not work. So if you have another PCB revision, maybe it will, just need some tweaks, another display driver or something like that. And other than that, it would be really interesting to also look at the wireless protocol and see if you can have like some buffer overflow to get code execution even without opening them, or just to have fun hacking stuff. And see you next time.